Yeah, hi everyone. Good afternoon, friends. Yeah, guys, can you hear me? Please confirm. Hello, guys. Okay, yeah. Thank you, Hemachandra. Okay, wonderful. Okay, we'll wait for just a minute or so. Okay, let's start. Hey guys, are you able to hear me now? Are you able to hear me now? Okay. Yeah, sorry. So comments, yeah, this doesn't show any alerts on the comments, right? So my team has actually intimated me that I'm not audible. So we connected back. Okay, let me just do a revision here. Yeah, screen is already shared. So hope you're able to see the screen as well. You're able to see the screen, right, friends? Please comment on that. Okay, you're able to, yeah. Only I think Srinivasa Rao has a problem. You can also connect on YouTube, Srinivasa Rao, or you can reconnect once again, refresh, and that should resolve the problem. Oh, so YouTube link is also been shared if you want to connect on YouTube. All right. So let me revise what I was talking about here. So we have 4 different stages of analytics, and based on what is your client requirement, you're going to proceed with those tools and techniques. Right here, the tool that we are using, R programming, right, is R programming. So using R programming, how do I analyze the data? Right, so data analysis projects. Whenever we talk about any analytics project, we need to see that it follows a certain process. Now that process is called as CRISP-DM. CRISP-DM is a project management methodology, isn't it? So here it has 6 steps. It talks about business understanding. Try and understand what your business is actually trying to, right, solve. What are their pain areas? What are their problems? We'll try to resolve them. Right, and then we will proceed further after identifying the objectives to the next step, and that next step is the data collection. We need data, right? Without data, you'll not be able to process anything. It's a data mining project, right? So obviously you need data. So data can be collected from primary sources or secondary sources. Then we'll also have to assess what kind of data we are dealing with, isn't it? Now, based on what type of data we are dealing with, we will proceed further using that particular techniques. I mean, whether it is structured data or unstructured data. If it is structured data, then the approach will be machine learning models. But if the data is unstructured data, then we will have to proceed with deep learning aspects, right? So similarly, what kind of data we are dealing with, right? The data types will tell us what logic or what policy we have to apply. But before applying any model, that is your machine learning algorithms, we need to do data cleansing. And as part of data cleansing, we've also learned about exploratory data analysis and feature engineering as well. Feature engineering is nothing but reworking on your features so that you'll finally choose what is more relevant, right? So here we have cleansing, we have outlier, we have missing values, then we have transformations. We discussed about discretization, binning or grouping, that is histogram, right? Then we talked about normalization, min-max rule, and standardization, which is standard normal distribution. Then we have discussed about dummy variable creations. So categorical data will be converted to numeric labels. And here we have labeling as well, right? Label encoding as well. And then we discussed about typecasting, we discussed about handling duplicates, and then zero and near zero variance fields. Based on what is the data and what are the things that we identify from the statistical calculations and of course visual representations, we will take an appropriate decision to clean the data. Next, we started with yesterday with bivariate analysis. We started with bivariate analysis. When we talk about bivariate analysis, we are dealing with two variables. Now, whenever we talk about two variables, the first thing that we will try to understand is what is the relation between them. Of course, you will have to do univariate analysis first. You take each of these variables, perform your univariate analysis concepts, try and understand the data better, and then come up with this graph. This graph that you are seeing, which is based on x-axis and y-axis, it's a two-dimensional visualization representation, is the foundation for all the visualizations that we had going to learn or we have seen. Because see, ultimately the computer screen which is being used for visualizing the data is a two-dimensional screen. Even though we are coming up with univariate data, the data that we are seeing has to be presented on x-axis and y-axis only. Okay, we have to take both of these. So scatter plot becomes one of the most important visualization technique. Okay, and yesterday we have discussed about what does the scatter diagram tell us. Let's see, you people remember what does a scatter diagram tell us? If you look at this visualization, what does it tell us? Or what is a scatter diagram? Definition of a scatter plot, friends. Yeah, yesterday we discussed about it. Definition of a scatter plot. Anyone? YouTube. People who connected on YouTube. Yeah. No one. Very good. Scatter plot. We discussed yesterday. Scatter plot is a visualization or visual representation of the relation between two continuous variables. It's a visual representation of the relationship between two variables that we are trying to see here. Right, so we have two variables, x and y, or x1 and x2. We plot this data on x-axis and y-axis, and this visualization will be helping us to interpret the relationships. Right? And what all things can we interpret from scatter plot? There are three things that we discussed. What are those? Yeah. The first thing is, what is the shape of the relationship? Right? Relationship is there, but what is that relationship? We are trying to interpret this. Here you will check for one condition. What is that condition? Whether the relationship between x and y is linear or not, is consistent or not. Whether it is consistent or not. Linearity means consistency. Then we talk about what kind of direction or what kind of effect does one variable put on the other variable. And here we are talking about two things. Direction could be positive or negative. Then we have the third thing, which is how strong is this effect of one variable on the other. And this effect can be categorized into three different levels. It could be strong, it could be moderate, or it could be weak. These are the three levels of the relationships that we can try and assess. So scatter diagram, of course, it talks about other things also, but these are the primary things that we need to look at this point of time from scatter diagram. Now, when we talk about relationships, right, using these relationships, we can try and do predictive analytics. We can come up with predictions. And that predictions is explained as y is equals to f of capital X, where capital X represents your input set of variables. So the features that we are taking in, the data set that we are taking in, will have multiple features. One of the features is treated as your variable of interest, and we have rest of the variables which are treated as input variables. Now we are trying to look at the cause and effect relationship between X and Y, where X is known as input variables, whereas Y is known as output variable. Input and output, and we can see various other names given here in input and output variables. Let me just find out if I can bring up that equation. Yeah. So let me erase everything that we have on the screen, and so base equation is y is equals to f of x, and y is known as output, but it also is known by all these different names: dependent variable, response, regressand, explain variable, criterion, measures variable, experimental variable, label, class. All these are different output variables, different names to your output variables. X is known as input. X is representing multiple input variables also, right? And here you have independent, explanatory, predictor, covariance, regressors, factors, attributes, carriers, controlled variables, manipulated variable, exposure variable. So these are all the different names that we give to output and, of course, input respectively. Output and input respectively. So refer to this book, guys. It gives you a lot of details. Yeah. All right, next. Now, machine learning is all about identifying this particular equation, isn't it? Machine learning is all about bringing in y is equals to f of x equation to life, to picture. So let me directly go to that particular concept where we see. I need to go a lot of pages. Huh? We're directly going to predictive analytics here. So machine learning is starting here. We are trying to look at scatter diagram bivariate analysis that we started with, right? So when we talk about scatter plot is talking about three important things. The first one is basically looking at, once again, basically looking at how strong is the relationship, right? Yeah, this is what we're talking about. Continuous data. So I'll explain this also. So scatter diagram is basically talking about the relationship, and you can see those different types of relationships can be interpreted. It depends on what is X and what is Y, how strongly one is affecting the other, right? So from the business perspective, from the data perspective, we need to interpret the data as, right, the cause and effect relationship. And we were looking at a few examples yesterday, right? Now, if you see a data which is falling like this, I mean, it is having a perfect straight line and going upwards. So we call this as a perfect positive correlation, right? There's no scatter at all. The data is not spread. All the data points are perfectly falling on that line. Whereas here, if you see, there's a little spread, right? Probably you might say it is a moderate relationship. If you see here, this is a weak relationship, isn't it? Here you have a curvy linear shape. Here, weak relationship, or you can say no relationship. You can draw a line like this, or like this, or like this, or like this, or like this, right? So there's no relationship. Now, direction can be negative like this. This is also possible. So when we plot scatter diagrams, we get these kind of visualizations. Now, from the visualizations, we will not be able to interpret whether the relationship is strong, weak, or moderate, right? So let me take the data set here. We were looking at the data yesterday. So this is my data. I created two variables. Yeah. This is my data. On the screen, you can see, just say plot of x comma y, and it gives us the scatter. And this scatter diagram, you can see that the data is falling on a perfect straight line shape. But if I take some other data, probably I'll take this. Yeah, this is iris data set, and here I'm taking two columns. This is the data. I will talk about, let's say, cars. This is the cars data, and this is my data set. Now, by looking at this particular data set, what kind of interpretation would you make on the data? Yeah. So I can clearly say that the shape of the data is having a linear shape. Of course, at a high level, we are looking at the shape of the data. Because practically, this is what you're going to see. Your data will not be perfectly lying on one single straight line, right? So there will be different kind of data points, and when you plot it, this is the shape that you're going to get. So from this shape, I would say that the data is having linear relationship, right? A straight line relationship. It's not curved, or it's not round or circled kind of thing. It's going in a straight direction, some straight line shape, right? You can imagine that you're drawing a line at the center, and this is the shape that you can interpret. Next, the second thing is the direction. Direction, very clearly you can say that it is positive direction, because as x is increasing, your y is also increasing, right? So it's a positive direction. And the graph also, you can see it is going upwards, right? The data is going to, right? I mean, it's moving upwards. So this basically says positive direction. Now talk about strength, guys. What is the strength? What is the strength here? Is it strong? Is it moderate? Is it weak? What do you? Is it weak? What do you think? You tell me. What do you think? Okay, somebody is saying moderate. Let's see what people at YouTube have to say. I'm looking at your responses on YouTube as well. I see only 1 or 2 people respond. Yeah. So I say I get mixed values. Some people are saying strong, some people are saying weak, some people are saying moderate. Which one should I consider? Weak, positive, okay. Positive, yes, we have already written that. Only talking about strength. If I talk about that, then yeah, I'll consider your weak as the relationship. Yeah, so I have 3 different types of strength here, right? 3 different levels of strength. So visual inspection is always tricky, because what I feel by looking at the diagram is my personal opinion, right? You can talk about anything. You might interpret that graph here in this graph, you might interpret this as a different thing, I mean different level of strength. I might say moderate or weak, or you might say strong. So difference of opinion will occur here. It is subjective in nature. Visualizations here are subjective in nature. Right? So if you remember, when we started to look at the data types, we discussed about qualitative data and quantitative data. So going back to the definitions of qualitative and quantitative. Qualitative data is a non-numeric data which can only be described. Qualitative data can only be explained, described. That is exactly what we are doing in scatter diagram. We are trying to explain. And my explanation might be different from your explanation. Your interpretation will be different from my interpretation. Then we discussed about quantitative. Quantitative data is the data which can be measured. Now, when we say measured, the numeric representation will be same for you or me. If I say 9, it will be 9 for you also. If I say 1, it will be 1 for you also. Right? So, to measure the strength, to measure this subjective value, which talks about the relationship between 2 variables, we use a calculation. That calculation gives us a constant value. That constant value is represented using small r. The calculation that we are going to do will give you a number, right? And that number is represented as small r. Now this small r is known as correlation coefficient. It's a coefficient, it's a constant. Coefficient means it's a value, right? Coefficient of correlation or correlation coefficient. That's the name for the measure of correlation between 2 variables. Right? So this small r has a very big formula, summation of xy into small your sample size minus summation, dot product of summation of xy, etc. Denominator will be very big, square root or something, right? So it's a big calculation. You do not need to remember the formula, not required. Okay, so that's the reason why I'm not talking about it. But interpretation of this calculation is very, very important. This is the measure of the relationship between 2 variables. Okay, and it talks about linear relationship. Remember, okay, it is a measure of linear relationship between variables. Correlation coefficient. It ranges from -1 to +1. Small r value ranges from -1 to +1. Okay, where symbol there, the sign that you are seeing minus or plus, that is talking about the direction. Ultimately, it is talking about relationship only, right? So the symbol that we are seeing is talking about the direction, positive or negative. Then the magnitude is talking about the strength, right? If I take modulus, I'm talking about magnitude, right? Not direction. So if I take modulus of this value, then the range is lying from 0 to 1. The magnitude, right, is represented as 0 to 100%, or we say 0 to 1. Okay? So remember that magnitude is talking about the strength, sign is talking about the direction for correlation coefficient. But how do I interpret whether the relationship is a weak relationship, whether a moderate relationship, or whether it is a strong relationship? How would I interpret using the small r value? We are quantifying it, fine, but there should be some limits, right? Some buckets or intervals. So this correlation coefficient has a thumb rule. Majority of the statisticians, most of them, they use a standard value which is modulus of r. I'm talking only about magnitude, right? If it is greater than 0.85, very strong number, very high in magnitude. That means I'm using the word strong, right? It is interpreted as strong relationship. Okay, it is interpreted as strong relationship. So anything which is greater than 0.85 is strong, right? Modulus of r, of course. So what about moderate and weak? Different people have different opinions there. It's not broadly practiced. We look for correlations which are strong, because that's how we can actually capture correlation between them, right? Correlation is nothing but here cause and effect relationship. Output and input, that's what we're talking about here. So correlation is measured using correlation coefficient, which is represented using small r. Range is -1 to +1. And anything which is greater than modulus 0.85, mod of 8 is strong. Okay, these are the things that you need to remember. Now you might say that I also want to define moderate and weak also. So you can, again, it's not hard and fast rule. Even this 0.85 is not fixed, because majority of the people follow it. We are also following it, right? We go by the crowd. So if you have modulus of this r less than 0.85, then we can consider it as not a strong relationship. Okay, but till what level we can consider this as moderate? So the best practices says 0.05 to 0.85. And anything which is below 0.5 is considered as weak. Yep. Anything below 0.5 is weak. Between 0.5 to 0.85, we consider that as moderate. Anything greater than 0.85, strong. These are only thumb rules, friends. It's not fixed. Only thumb rules. Okay? Right. So that smaller is calculated using a formula. Big formula, not required. In R, it can be done using COR of correlation is measured between two variables, right? You can represent that as x comma. This is your R value. Let us look into the R calculation for all these scatter diagrams that we have come up with. So we will start with the first one, which is the sample data that we have created, which has a perfect straight line. So what should be my small r here for this particular visualization? What should be my correlation? How should be my, what should be R value, friends, here? So function in R is correlation, comma, X, comma, Y. Yeah, what should be my R value? Anyone? Yep, that's correct, Kashyap. Remember, it is a perfect straight line where the entire data is falling on the straight line, right? So no deviation at all. So this correlation between $S1 comma $S1 Y, X comma Y, right, is going to be perfect 1. Here you can see it's perfect 1. Now, if your data is spread away, the spread is more, that means the strength is decreasing. So I'll come here. For this particular iris data set, I'm going to measure correlation. Correlation between sepal length, petal length. Now, if you look at the visualization, our interpretations could be anything. We can say that, hey, it is a kind of curvilinear. Here I see straight line, but here I see no relationship. But if I combine all this, I get a kind of curvilinear shape. Right? This is something that I can see. But if I have to consider everything like this, then the relationship is very, very weak. Right? That's my interpretation. So what about the mathematical expression? Correlation between X comma Y. So it says 0.87. 0.87. How do I interpret this relationship, friends? I'm taking only 2 decimals. So how do I interpret this relationship between the sepal length and petal length? What do you think? How do we interpret the relationship? Strong relationship. Very good. The symbol that you are seeing, the sign is positive. And the thumb rule says if it is greater than 0.85, then we have to interpret it as a strong relationship, right? So here we are saying it is a strong relationship. Right? From subjective eyes, from the domain knowledge perspective, this might be different. The relationship might be different completely. But from the data perspective, from the statistical computing perspective, the relation between sepal length and petal length are strong. Because it is greater than 0.85. This is how we interpret. So the previous one is also very strong, right? It's perfect 1. So it is strong relationship. Here also we get strong. Now let's look into this CARS data set. Here I have plot. Okay, let me take this. This is the data set, CARS data set. So as we discussed, it is like subjective, right? It was moderate or weak. Some people were saying moderate, some people were saying weak. So let us try and plot this. Correlation of cars, dollar, speed, comma, correlation, so cars of distance. Correlation of speed versus distance. What is this relationship? The value is given here. 0.806. Here I'm taking 3 decimals just to show that it is 80.6 or 0.8. 806. By looking at this number, we can see that the relationship is positive because the direction is going upwards here, and the symbol also says positive. And it is moderate. The value is less than 0.85. Right? So this is how we measure the correlation. Scatter diagram is only a visual representation, whereas the correlation coefficient is a mathematical calculation which measures the correlation. But always remember, correlation does not guarantee causation. Correlation does not guarantee causation. What does this mean? Yesterday we discussed about an example, if you remember. If I take any two random data point variables, ice cream sales, and here I am talking about sharks attacking people, shark attacks. It has nothing to do, right, with ice cream sales. Ice cream sales is not affecting shark attacks. These are two independent variables. But when I'm plotting it, I might get a perfect shape like this. It's just two numeric values, right? So I can come up with scatter diagram. I can also do a R calculation. Both are representing, scatter diagram and small r are representing the correlation between two variables. Remember that. From the data's perspective or statistical perspective or mathematical perspective, these two are calculating or explaining the correlation. But it doesn't mean that you will have a perfect correlation, cause and effect relationship between these two. No. Right? So this is something that you have to remember. Correlation does not guarantee causation. Right? Now, for predictive analytics, if you have to do the predictions, remember that this variable that we are talking about, the data points that we are talking about, should actually have some kind of an effect on one. Right? If it doesn't have effect, then logically you cannot explain. Isn't it? Hence, we need to first interpret whether the relationship between the variables is there or not. That's very, very important for us first. And if you feel that yes, there is a relationship, only then we will proceed with the scatter diagrams and correlations and all that to understand what kind of relationship it is. Not the other way around. Okay, first do scatter diagram, then calculate correlation, and then try to interpret relationship. No. If you try to do this, then you get shark attacks and ice cream sales. You end up getting those irrelevant variables for your analysis, which is logical, illogical. You cannot explain them logically, right? So be careful from that perspective. That's the reason why you need to understand the data better. Understand the data with respect to the business better. Right? So that's about relationship, guys, bivariate relationship. We'll also have to extend that to multiple variables also. But when we say multiple variables, again, remember, the screen that you are seeing is a two-dimensional screen only. Right? So you can only have x-axis, y-axis. That means you take two variables. We might say x1, x2. That x2 could be y also. Okay? But if I have multiple variables, then how do you analyze the data? Because after all, your computer screen is a two-dimensional screen. right? What would you do? So we basically talk about, or we're talking about multivariate analysis. The simplest other visualizations like heat maps and all that. What we are doing is a very simple approach, simple logic, which is basically converting this multivariate data into bivariate data and then analyze those bivariate data points. So here we create pairs. So we'll say x1, x2, x1, x3, x1, x4, so on and so forth, and say y and x1, what is the relationship? Similarly, you talk about x2, x3, x2, x4, so on and so forth, and then you say y and x2, right? So this way, we are converting your multiple variables into bivariate case. Visualization is also done the same way. For example, here, I will be loading this data set. Okay, let me take this data. So load card, load the libraries card, then load the data set salaries. This is the salaries data set. I have multiple variables, right? If I take only two variables, that is fourth one and sixth one, then I get this one, right? Sal. Yesterday we have done this. Now, if I need to take, let's say, PhD also, right? Let me add one more data point here. 3 comma 3 only, right? 1, 3, 4, yeah, 6. So if I am taking 3 columns, that means it's greater than 2 columns, right? Now using these 2 columns, that is x1 and x2, let's say this is x1, this is x2, can I predict the salary? So we are trying to understand the relationship here. So to interpret this relationship, you need to basically come up with, analyze the relation between x1 and x2 as well. So these are the pairs that we can create from this 3 features. Now those features or these pairs can also be visualized. So if I say plot and take 2 variables, then this is what I'm going to get. But I will say plot of multiple variables. So let me take this to the bottom. Just arranging the code properly. Right. So this is your bivariate data, and here I am saying plot of SAL. SAL is your data set which has 3 columns. You can see that here. You're referring to 397 rows, but yeah, 3 columns. So when I do plot, it gives us the multivariate visualization. Same function, but here you are now passing, right, the 3 columns. So on the diagonal, you can see it is just representing the names. Okay. Now, how do we read this visualization? If I take the visualizations on the top of this particular diagonal, then here you can see this is x-axis where I have years of service plotted. This years since PhD is this y-axis. So I'm plotting x and y there, treating this as y, this as x. The same visualization, right? If I do a mirror image, that means years since PhD is becoming x-axis, whereas years service becomes y-axis. Right? So it is mirror image. Same way here also, this is the relation between years since PhD and salary. The same visualization can be seen here. Just a mirror image. Right? So this is basically your pairs plot. Plot is the same function which is used. Plot, plot. But when you plot, when you try to plot or when you try to pass this function with two variables, then it is going to take scatter diagram as the output, or it is going to give you scatter diagram. When you pass multiple variables or a data frame, then it is going to consider that as a pair plot. It is called as a pair plot. This representation is called as pair plot. We can also have pairs. This is also same as your plot. No difference. Same visualization. Yeah, same visualization. So either you say plot or you say pairs. It's going to give you pair plot. If you pass plot with a single variable, then that is going to give you a dot representation, line representation. Right? We have done it in line chart if you remember. Right. So these are right, the preliminaries that you need to remember for your multiple variable analysis, multiple data variable analysis. But this is only from perspective of scatter diagram. How about measuring the relationship between multiple variables? To measure the correlation between x and y, we used COR, right? And we passed COR of x comma y. Did I do that? Yeah, I did it, right? COR, correlations, x comma y. So how about doing same logic like scatter diagram? For scatter diagram, what did we do? We said plot. Plot of x comma y is a bivariate visualization. Plot of the entire data set is nothing but your pair plot. Right? Same way, I can use correlation with the entire data. I can do correlation on the entire data. Just like you get pair plot, correlation function also is going to treat pairs. Right? It is going to create pairs and calculate that correlation. The output is given in the console. Just like this, okay? Just like this. Here also you get the pairs calculation. Diagonal value will be 1. Why diagonal is 1 here? Because it is calculating the correlation between itself. Right? It is the correlation between itself. Hence the diagonal is equals to 1. Right? Next, if you want to look at this correlation, the correlation is between years since PhD and years service. So you can take either row like this or you can take column. Okay? So if I read column wise, so relation between years since PhD with years service is this much. 0.91, approximately 0.91, 9096, so I'm rounding it off to 9. This is the correlation, right? And similarly, if you look at this visualization, That is the relation between years since PhD and salary. So the same column, if I talk about salary, then you can see the relationship between these two is weak. Less than 0.5. So I'm interpreting that as a weak relationship. Right? So this way we interpret the correlations. Right? Yeah. Is this calculations clear? We are trying to understand the bivariate analysis a little deeper. So we are measuring, quantifying the relationship as well. Now, question to you all. What if R equal to 0? Yeah, let's see how many people will answer this. What if R is equals to 0 between X and Y? How should I interpret that? Let's see if I have. There is no relationship. Very good. There is no relationship. Carl Pearson correlation rank. Shashidhara, we are not deep diving that level. Okay, this is Pearson correlation. You can imagine that this is Pearson correlation. That's it. Let's not get into too many things and complicate things. So we can say if R is equals to 0, that means no correlation. But can you imagine how would the diagram look like? Because we are trying to map the magnitude of the relationship with the visualization that we got in scatter diagram. Right? If you see here, the scatter is too much and the direction is also kind of getting slanted. Whereas here the relationship is like very close. The data points are very closely scattered. Right? So what kind of a visualization would you see if R is equals to 0 between X and Y? If I draw a scatter diagram between them, how will my data look like? Visualization. I'm talking about scatter diagram. How does scatter diagram look like? Yeah, that's the interpretation. No relationship is the interpretation. Can you explain the line? Can you explain the scatter of the data? Each one's okay. Okay. So the correlation is 0. That means there is no cause and effect relationship. I'm saying no cause and effect. That basically means this is input, right? We're talking about this as input and this as output. So irrespective of whatever changes you're making in your input, there is no effect on output. Say for example, this is your output. Whatever your changes are for X, Y will remain constant. So if R is equals to 0, then you will see a line, the pattern basically, the line which is parallel to X-axis. A line which will be parallel to X-axis. Right? Because we are talking about correlation between X and Y, X causing an effect on Y, right? But if you remove that, then you can also see a line which is parallel to Y-axis also. That means different values of Y, X is same. Okay? But yeah, we do not talk from that perspective because input and output is clearly defined here, right? So X-axis is your input. So irrespective of whatever the changes that we have on our input data, output will not get affected. Alright? So this is how we interpret the relationship between two variables. Right. So hope the relationships are clear. Any questions pertaining to the discussion? Yeah. Okay, I see no questions. All right. Yeah, all these things are discussed in our book, friends. Right? Hope everybody has got their access to the books. Yeah, if not, then please do get it and do participate in the social media activities. There are a lot of quizzes, a lot of events that we are conducting, right? So do participate in this. All right. So we will take a short break now. We'll come back and talk about predictive analytics that we started yesterday. Okay, we'll try and understand the terminologies, try and understand what is the logic behind the scenes and all that. So right now the time is okay 3:05. So we'll come back in 10 minutes at 3:50. This is the break timings. Niharika, book is there on the website. So you need to search for 360digitmg.com. Okay. When you visit the website, you see these learning resources. You need to click on that learning resources. And here, when you scroll down, you see the digital book. This download option is for you to download the version that you will be working on. Access now will give you the online book like this. Okay, just browse through the website. You'll be able to get that access. Right. And yeah, these are the videos. It's there on the YouTube as well. You might want to access that. These are the past videos that we have covered, right? Our programming. All right. So let me talk about a little bit of overview here before we proceed for regression analysis. So we're talking about predictive analytics. Okay, so all this while we discussed descriptive, now we are coming up with predictive analytics. And in predictive analytics, like when we talk about machine learning has both descriptive and predictive. We're talking about predictive. We are trying to predict a value given the set of equations, right? This is your base equation. Now this approach are called as supervised learning techniques. These are called as supervised learning techniques. Because ultimately you're trying to train your machine so that it figures out the relationship between X and Y. Right? So if your computer, if your machine has to understand the relationship, then in the historical data, right, when the algorithm is trying to train so that it identifies the pattern, it should upfront know what is the Y value. So here you'll have X1, X2, X3, X4, for example, and then you have Y. Then given the bunch of inputs, X1, X2, X3, X4, then what is Y? You upfront know this, right? So you're saying, hey, given these set of values, I'll get this Y. Given these set of values, I'll get this Y. So on and so forth, you're training. So the pattern in the data can be identified by the algorithm with the known Y. So we say Y is known. And we're doing predictions here. Predictions of Y. Right? Now, when you know this data set, when you know what is your output column, we would be able to learn whether this data is qualitative or quantitative, right? Numeric or non-numeric. Based on what is the value that you are trying to predict, your equation would vary. Your approach would vary here, right? But ultimately, I need the base equation to be identified, which is y is equals to f of capital X. Now, if this is numeric, right, we are saying whether it is continuous or not. Okay, we've already discussed what is continuous and discrete. Please refer to the previous videos in order to gain more knowledge on that. So you're talking about data is whether continuous or discrete. Now, if it is continuous, that means the data has any value. It can take any value on this x-axis, right? That's your input. And your output can also be anything. We are talking about y being continuous, right? So this value can be anything on the y-axis, given the x-axis, right? Now, in order to solve this, we are applying something called as linear regression method. We are regressing the output using input variables, input values. Okay. Now this is nothing but equation of straight line, guys. If I have to explain it in a very simple terms, you're talking about equation of a straight line, right? If you have fixed values, if it is discrete values, then you'll get dots. But this is continuous value, right? It could be anything on this line. It could be any line. That's the reason we are drawing a straight line. Okay? And yesterday we have seen how we get this data, right? How we get this equation. If I talk about x and y as an example of 0, 1, 2, 3, 3, 5, 7, 9, right? We get something like this, right? So this is 0, 3, 1, 5, 2, 7, 3, 9, so on and so forth. But your x can be anything. Okay, x is also continuous, mind you. X can be anything. So it could be 2.41 or 45. So if your x is 2.45, then what should be your y? I don't have that information in my data, right? So what could be that? So in order to figure that out, we are getting this equation. Y is equals to mx plus c. And in order to get this, we'll substitute these values into the equation and we'll figure out the equation. Y is equals to 2x plus 3, right? This is what we got yesterday. So we are cross-checking. Let's cross-check this. If I substitute 0 into the equation, what would I get? I would get y as 3 only. I'm trying to draw the prediction values. And remember, predictions will have this hat symbol. Okay, this should have hat symbol. So I'll say if x is equals to 0, y is 3, y hat is 3. If x is equals to 1, y hat is 5, 7, 9. So that means you are predicting the data exactly on that line. And your data is also falling on that line. Right? So your equation is perfectly fitting the data. But do you think in reality this would be the case? We have seen multiple diagrams there, right? Here in this data, in fact, we have seen so many different visualizations, right? So if I take, let's say this visualization, I'm talking about speed and displacement. Can I perfectly fit a line like this, which is passing through the data points exactly such a way that it is covering each and every data point? No, right? Not ideal. But we are trying to come up with a mathematical equation, y is equals to mx plus c for this equation. So what we need to do is try and identify the line which is passing through the data in such a way that it is giving us the best fit. Best fit means what? It should be able to give us this y when I substitute x as close as possible, right? It has to give the value of y as close as possible to the original data. But I have to treat this entire data set as one big unit, one big set. And this equation has to represent the entire data. Remember that. It's not representing each value there. It's representing the entire data set. Remember that. Right? So considering the entire data, I need to find the best line. How do I do that, guys? If this is my data set, how do I get the best line? We can do one thing. See, I want the best fit. I want the best fit line on my data. That means this equation should be satisfied, right? Whenever I pass x, y should be optimal. But as I said, ideally it will not happen. But if it happens, then the line is satisfying the entire data set. This is representing for the entire data set, right? If you are predicting the value correctly, right, we just discussed that in the previous example. If I have this, if this is the data, this is what I got, right? So if you look into the prediction value and the actual value, observed value, there is no deviation at all. That means there is no error in your prediction. You are predicting this, but you predicted it as your original value. So this error is nothing but the deviation in your prediction compared to the original data. And this error is 0, right? But in original reality, if you look into this kind of data set, it will not satisfy the data. Each and every data point will not be satisfied. Probably one of the data is falling on that line. For that one value, it will be 0. But rest of the other values, it will give some deviation, right? But if I have to say best fit line for this entire data set, then error should be 0 for the entire data set taken together. That is nothing but representation of this error for the entire data set should be equal to 0. And representation is nothing but average, first movement, remember? So the property of your linear regression is to find out a best fit line. And when I say best fit line, it is giving the average of errors as 0. So find the line which gives us the average of errors as 0. That means it should pass through the center. Okay, but passing through the center can happen like this. It 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 can happen like this. N number of different lines are possible where you get summation of errors as 0. If summation of errors is 0, average is also 0, right? Because average is nothing but sum by total. So if sum of errors is 0, your average will be 0. So n number of different lines would be possible here. Among all this, you need to find out the best fit line. That means the line should give us the least deviation or least variation or least error. But how do you get that least error? When you're taking summation of error, it is giving us 0, right? That is the least value, right? So in order to measure the magnitude, we take squares. So what do I need? I need least squared values, least squares. So the process that we are trying to understand is called as OLS, which is nothing but ordinary least squares. Ordinary least squares. OLS. Yeah. What is this OLS doing? It is trying to find out a line which is giving us the least magnitude of error. That means this line is passing through the data in such a way that it is as close as possible to each and every data point. So how do we measure that? So we take, let's say, one line. I'll draw a line. This is one line. From this line, we measure the deviation of each data point, the original data point that we have, right? We are measuring the deviation of each data point here. They are in the same line, so yeah, that's the reason why you are getting overlap values here. But this is how we measure the deviation of each data point from that line. Because when you're predicting, your predicted value will be on that line, right? So this is a data point and we are measuring the distance among this data and this data. This is your actual value and this data point is your predicted value. Okay, the value on that straight line is your predicted value. So error is measured as what? This deviation. That is nothing but actual value minus predicted value. And we're taking squared of these distances because few data points will be above the line, few data points will be below the line. When you add, it becomes a 0. So what you're doing? You're taking squared errors. Summation of squared errors. It is nothing but your variance, right? So we take sum of the squared values and then we record. Let's say this is line 1 and we are getting least square errors. So let's say this is what? Sum of squared errors, right? And we take okay, mean squared error. We're taking average of squared errors. We'll record that. Let's say this is MSc 1. We take line 2. Let's say line 2 is passing through the data like this. Again, we're talking about another line. Okay, let me draw that second. Okay. Let me change the color. And let's say probably this is my another line that I'm drawing. So from this line also we measure the distances, right? So let's say this is line 2 and we get MSc 2. Then we take MSc 3, line 3, MSc 3. Then let's say line 4, MSc 4. So on and so forth. Out of all these calculations, all these lines that we are getting, we need to pick the line which is having the least distances, because that would be the line which is passing through the data points in such a way that it is as close as possible to all the data points together, right? This concept is called as OLS, guys. Yep. Is it make sense, the OLS concept? Any doubts here? We'll take one data and discuss this, okay? Yeah, we do have certification, Niharika. We can discuss that later. Any questions? I'm looking at questions related to the subject, guys. Okay, I'm not seeing any questions, so let's proceed. Let me take this particular example, okay? I'm talking about this example. We've already discussed. This is S1. This is my data set. And my data set, you see, a perfect straight line will be obtained. So let me execute that plot. And correlation is perfect 1. Now on this, we need to come up with visualizations. I mean, equation of line. Now in R, in order to get the equation, what is the equation? Y is equals to mx plus c, right? We need y is equals to mx plus c. Now, this is basically rewritten in different forms. I would write this as beta naught plus beta 1 x. This is the expression that I use, where beta naught is nothing but c, beta 1 is nothing but m. This is called as intercept. This is called as the slope. And together, these are called as parameters, or they are called as coefficients of your equation. or they are also known as estimates. Okay. Now, if you know what is M and what is C, your equation is solved, right? So we need to find out that equation. So that regression is done using a model called as a function called as LM. LM basically means linear model. Okay, that's LM for you in R. So question mark of LM. Fitting linear models. Linear models is the straight line that we are talking about, right? We're trying to do that. So let's say we are recording this as model 1. Okay, we are trying to save the details of the calculations that R is going to do on the data set. So I'll say lm y tilde x, that's the syntax. We want to regress y on x. So this the syntax is lm y tilde x. Y tilde x. So that's exactly what we have done. And we are saving the data that is obtained by this calculation into a variable called M1, model 1. So we have successfully created your model. So if you just say M1, so you got the intercept and the slope axis. Intercept is C, right? So is the coefficient of x. So we got y is equals to mx plus c equation. Let me put that. Y is equals to m is 2x plus 3 plus 2x, whatever that you want to write. So that's the equation. But if you see, m is a variable which is having a lot of calculations in it. It carries 12 different calculations. And in R, if you want to refer to any of these sub values, then we put dollar. Like here you can see table name, S1 is the table name, $1, S1 $x, right? Similarly, we did the previous one also. Dollar, table name dollar, right? Table name dollar. So same way we are putting M1 dollar. And it gives these different calculations that we did, right? What you're seeing is coefficients. We also have residuals. We also have rank, fitted values, QR, DF residuals, all these things are there. Now what you do is you simply say summary of M1. You say summary. Now summary is a function in R which is going to give you the detailed summary of the various values that particular variable is holding. The data, summary of the data. It's like your pivot table concept, right? When you say pivot table, it gives you description or summary of your data. Same way. But here we are not talking about data, we are talking about some calculations. M1 carries 12 different values. So for each of that value, it tries to give us the summary. Let me explain what is the summary. So understanding the output of linear model is very important. What are various things we need to look at to interpret or to validate the equation? This is the equation. This is the formula that we apply. Then residuals are nothing but leftovers. What is leftover? You are trying to regress y using x, right? So when you're trying to regress, you are trying to reach y. But you could reach only till this. So what is the leftover? That's your error, or we call it as residual. What is this number? You have 6 values because your data set is of 6, right? Data set is of length 6. The 6 records are there. So for each record, it has calculated error also, because you are able to predict now. You have the equation, right? So you have x, you have y, you have y hat also. That y hat is this. Y hat error is this. But what is this error? How do I interpret this? 1049 e power minus 15, exponential of minus 15. That is 1.049 into 10 power minus 15. Right? This is written as like this. So this is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is your value. This is your error that you are getting. I can simply say equal to 0. Right? So the first error is 0. Second error is also 0. Third error is also 0, 0, 0, 0. Right? Because it's a tool, it is calculating at a very, very high, right, accuracy levels, and it is able to get these things. But ultimately, for naked eyes, it is 0. Right? So that's your residuals, errors. Then we have seen coefficients. So your equation y is equals to mx plus c that we are writing, or you say beta naught plus beta 1 x1, can be rewritten like this. You have estimate, intercepts, and slope. So y hat is equals to 2x plus 3. This is your intercept, this is slope, mx plus c. Right? And when you substitute x value, you get y hat, and you'll be able to do the calculation y minus y hat to get the error. Right? And there are certain statistical values that we need to look at. So one of that is this p value. PR is basically talking about probability. Okay, and this value that you're seeing, as per the standards, I'm not going into the details of these points, but as per the standards, this probability value that you're seeing, the p value that you're seeing, should be less than or equal to 0.05. I should say less than 0.05. Okay, this is nothing but 5%. Okay, the p value is called as the chance of going wrong. It's known as significance level. We are not going to go further any depth into this. Just remember that it is the chance of going wrong. And industrial standard says you should have not more than 5% chance of going wrong. These coefficients, when they are calculated, the chance of going wrong is this much, which is less than 0.05, which is less than 5%, right? So accept that. Right? That's your regression value. Then we also have something called as R squared. We'll talk only about multiple R squared. Okay, we're not talking about adjusted R squared. One thing at a time. So this multiple R squared is called as coefficient of determination. Coefficient of determination. Okay, it is represented as R squared. It is also known as predictability or goodness of fit. Okay, and it ranges from 0 to 1. R squared, right? It cannot be a negative value. It can range from 0 to 1. And this R squared is basically expressing on how well can you predict Y given X. And if it is, you can see here it is 1. This is 1, right? 1 means you are able to predict perfectly. If I have X And if this x is varying by some percentage, then this is causing an effect on y, right? Cause an effect on y. How much of that variation in y is caused by this variation in x? Right? We are able to capture 100%. That means y is changing because of this, right? Change in x. And that change in y is 100% caused by this. So we're able to capture that variation. Right? You can also imagine that this is the goodness of it. That means if you have data, how much percentage of the data is falling on this line? The equation that we came up with, right? And you can see that 100% of the data is falling on that line. That's what we have seen right here. You've seen 100% of the data. 100% of the data will fall on that particular line. Yeah. So that's basically your equation. Yeah. But what you need to understand is, if in reality the data is varying a little, so what I'll do is I'll show you same content, but let me change this a little. Okay, I'll change a little. Probably I'll say y is equals to 10. So I'll call this as A, this as B. Okay, and I'll call this as S2. Yeah, so I'm creating another data set, S2. And if you see S2 here, the data point is slightly moving. If you see near 3 in the plot, observe carefully, this data point is moving. That's the only change I made between S1 and S2. Okay, now given this spread, because it's not perfectly falling on a straight line now, I cannot draw a straight line which is gonna pass through all the data points. I'm very bad at drawing. I cannot get a straight line which can pass through like these lines, because this will be left over if I draw a straight line like that. If I try to get this, then this will be like this. It will not be a straight line, right? It will not be a straight line. Yeah. So in this case, what will we do? If you go with the regular logic, which is substitute this data point, this is your first data point, substitute into y is equals to mx plus c, you'll get y is equals to, or c is equals to 3. Then pass 1 comma 5, that's the second data point. If you do that, you get m is equals to 2. So your equation will be same. Y is equals to mx plus c will be y is equals to 2x plus 3 only. But if you do that, then you are getting this data point. Right? Now remember, the properties of this regression line is that this should give us average of errors as 0. Right? Now if I talk about this scenario, I'll have, so A, B, right? So I'll say B hat. This is 0, 1, 2, 3, 4, 5. And here I have 3, 5, 7, 9, 11, 13. So when I use that same equation, y is equals to 2x plus 3, that is b is equals to ax plus a, 2a plus b, or 2a plus 3, you get this same values. This was 10 actually, my data set is 10. But here you get 9. So you can see this data will be deviating. So if I measure error here, which is the difference between these two, this will be 0, this will be 0, this will be 0, but here I get 1. So when I do average, which is sum by total, I get 1. I get some other value because sum of the errors is 1. So average, I will get some average, right? 1 by 6. So this model cannot be accepted because it is not representing the entire data, right? You're ignoring this data point. So it is deviating from the property of the equation. So I need to come up with a line which is trying to give us average of errors as 0, right? And it cannot discount this data point. All the data points are equally important. So we will come up with a line which is passing through the data like this. Thereby, it gives us some deviation here. And when you add all this, it becomes 0. Right? So let's see that. I'll show you here. So correlation will also be a little different. It will not be perfect 1 because one of the data point is not falling there. So you get 0.99. So if I do LM again, S2$B tilde S2$A. You're basically representing X as A, Y as B, right? So I'm just rewriting that. And I get M2. Now I will do summary of M2 fields. What did I get here? We'll first look at residuals. Is this 0? No, it is not 0. Is this 0? No. Is this 0? No. No. So if you look into the coefficients, which is basically giving you this equation, your y hat is explained as mx plus c. So what is m? 2. 2.0286 into a plus, this is b, right? So I'll say b hat is equals to, what is c? 3.0952. So if I substitute the first value, which is 0, 3 into this, what happens? If I pass only a here, then this becomes 0. Your b hat will become 3.0952. And the error is b minus b hat, which is minus 0.0952. That's what you got. Yeah? That's what you're getting here. So the line is passing through the data in such a way that it is balancing all the data. Right? So your OLS technique is trying to find out the best fit line. The best fit line is basically giving us a line which is having the least squares. Least squares, distance from the data to the line. Least squares, errors. Right? Now you can see residuals. Residuals are available under M2. So you need to do mean of M2 dollar residuals. If you do that, you get 0.0. E power minus 17, right? So those many zeros are there before your decimals. So it is nothing but 0. right? But if you take y is equals to mx plus c, which is 3 and 2 as your coefficients, then you'll get average of error as 1 by 6, sorry, right? So that should not happen. Is this OLS concept clear? Now this is what is used for your linear regression, friends. Now what schedule a job? I didn't understand. Schedule a job? What job? You're doing analysis, Jyotsna. It's not an application that you're developing. Here we are doing R&D. So we are taking data and we are trying to experiment on the data. Yeah, so there's nothing like creating a job and all that. That's not what we see. Right. Yeah, any questions in OLS? Finding out the best equation, which will then be used for prediction. Any questions? Okay, so we will wrap up for the day, and tomorrow's class, we are going to see how do we fine tune this equation. We are getting one equation, fine, but can I adjust this equation further so that it fits even better? Right? Not every scenario would be so ideal. Okay, nobody's interested in what I'm talking about. I think everybody is very much interested in this. Let me ping that link. Yeah, so you have that link, guys. Okay, yeah, I pinged the attendance link. Please fill in your attendance. All right. I see no questions. All right. So yeah, if you want to go through that OLS technique a little further, you have those concepts here measured, okay? So we will be talking about a few more things here, and we will probably jump on to the textual data analysis later once this is completed, okay? So we'll see how to handle text data. But go through this book, guys. The concept that we discussed is written here, OLS. All right, friends, thank you so much. Hope you understood the concepts, and yeah, take care. Bye-bye, friends. We'll see you guys again tomorrow. Thank you. Okay, T question, is it? I see question. P-value fishing. Oh, okay. If I have to discuss all those things, it will take a lot of time, Niharika. We'll not have that kind of time. We need to discuss a few more things also. So interpretation is what I've explained, right? So always look into the summary of your regression. When you see the coefficients corresponding to those coefficients, you will have p-value, the last one. All you have to see is this p-value less than 0.05 or not? If it is less than 0.05, only then consider it. Otherwise, we will basically try and transform the data. That's something that we'll cover tomorrow. We'll try to see how to better the equation. Okay, what manipulations we need to do. All right. Yeah. All right, guys. Thank you all. Thank you.